We see this also in big data analytics and clustered applications. So there's a paradigm shift from simple client-server applications to truly distributed applications, which many people in the Erlang community have been well aware of for several years. That's starting to appear in the mainstream enterprises and organizations around the world as the network becomes more strategic. But that creates tremendous challenges for managing that kind of connectivity at scale and providing the kind of reliability and performance that are going to be required. So just imagine, excuse me, just imagine a Hadoop data processing type engine, distributed engine, just like you'd find with a Erlang-like cluster. You could have instances in different countries. You could have data spread all around the world, and given the multi-core options we have for platforms, how do we scale this to really, millions of cores and tens of thousands of nodes distributed across a very large organization? At Infoblox, we have a similar system in our grid, but we think of this as a general problem in scaling large-scale distributed data-intensive platforms. That's one of the things that brought us to look closely at Erlang and find that even with the tremendous properties of a platform like Erlang, there are still emergent problems in networking to get such a system to work well in a widely distributed sense at scale. So how do we scale a thing like that? Well, if we look at Amazon and Google, I think there's a good understanding of how to scale in the data center and how to scale in distributed organizations. That hasn't necessarily gotten to the mainstream products that are available through open source or otherwise, but there has been 10 years of understanding how to get to million core type scale in only a couple companies around the world. And as we all know in this in the Erlang community is a well-known advantage of Erlang, the models for achieving this scale requires a model that all hardware is just failing all the time. So, maybe we're at a paradigm shift from, the Java world of write once, run anywhere. I think to tackle the complexity and the scale that we're faced going forward, something like write once, run forever. Of course, until you want to change the code. And so if we look at companies like Google and Facebook, and we recognize that most companies in the world don't want to be the largest search engine company, but they certainly have pioneered networking techniques that allow network to continue to scale with the rest of the compute and storage infrastructure to attack distributed applications like a large search engine in a cost-effective manner. And in fact, these organizations, Google, Yahoo, Deutsche Telekom, Verizon, have actually come together to share their knowledge with the world in an organization called the Open Networking Foundation. What's striking about this organization is that it's a standards body that is responsible for some critical standards in the emergence of software-defined networking. As we all know, software is always been the way to combat complexity at a reasonable cost. So the Open Networking Foundation is driving leading standards in software-defined networking, but it's not a vendor-driven organization. It's driven by organizations that have real experience in scaling networks to the levels that are going to be demanded by the mainstream enterprises and organizations over time, taking out of just the cloud apps and really into mainstream networking. The primary standard that the Open Networking Foundation has been pushing is something called OpenFlow. And I think the easiest way to talk about OpenFlow is if Ethernet has, I think, very arguably become completely ubiquitous. Yesterday I was on a panel at the 40th anniversary for Ethernet at the Computer History Museum here in Silicon Valley. And it's really tremendous, the statistics of what percentage of ports that a company like Cisco ships that are Ethernet. In the 90+%. That means Ethernet won. And OpenFlow simplistically is a remote programming interface to Ethernet data paths. I'll talk a little bit more of that in detail, but basically what it means is that if you have an Ethernet-enabled network white box, remotely, you can turn that white box into a firewall, a load balancer, a switch, or some combination of those network processing functions that are tailored to your specific application, and you can do that across, 100, 1,000, or 10,000 switches with a remote programming interface, OpenFlow. And this is not a science experiment. It's in practice and working in some of the largest and most traffic-intensive environments deployed in the world today. So, given my involvement in OpenFlow and the Open Networking Foundation, many people ask me, what is software-defined networking? I generally say, I'm not sure that's the right question. I think the right question is, what is hardware-defined networking? And the striking thing is, hardware-defined networking is an entire industry organized along box function lines. So typically, for many appropriate reasons, for the last 20 years, we've thought of building a network as we have to buy load balancers, firewalls, WAN optimizers, and routers and put them all together to make something work. That has worked well, but the reality is that as we scale, the complexity of managing that environment becomes the real barrier. It's no longer about bandwidth, it's how we manage the vast complexity of all those boxes and their different functions and APIs and programming models and deployment models that are all vendor specific. It just doesn't work at scale in a cost-effective manner. And also, underneath the hood, all these boxes today are essentially the same. Fast, cheap, and Ethernet, which means the consumers aren't really getting the value of that inexpensive hardware in the same way you would get in servers, where the real differentiator today technically is already in software, but we don't buy network white boxes like we buy servers today, and we're not really buying any independent software like we buy independent software on servers today. That's the paradigm shift that SDN is, really a market correction where the center of value moves from hardware to software in the networking industry, giving rise to new products on the software side, new capabilities, and the ability to scale networks well beyond what they can do today from a cost perspective. And again, as we Infoblox knows something about large-scale data-intensive systems, since that's what our grid is, you can imagine options we have today to scale the core, for instance, include InfiniBand, but OpenFlow over Ethernet, which may have properties very similar to InfiniBand, look much, much better from a cost perspective. And for those of you deploying Erlang applications, certainly some of the core networking issues you can imagine remain potential bottlenecks in scaling those. So we're very excited to work with Erlang Solutions and Erlang on software-defined networking solutions for scale. So again, hardware-defined networking says the control plane is bought with the box. It's embedded in the firewall, router, or load balancer, and then you may have some sort of vendor-specific management plane. In SDN, we say all you have are network white boxes. On this slide, vendor A, B, and C data planes are just Ethernet processing boxes, And at runtime, they can be turned into firewalls, load balancers, or routers on a per flow basis, and any combination of those. And there's a standard interface that talks to control plane software, the blue box on this slide, and that can live anywhere. And that's a fundamental difference. Internet style networking demands a certain kind of control plane embedded in the box, and OpenFlow networking says we have a huge design space of control planes, so we can have many different ones, and they can live off the box. And that's a major paradigm shift in terms of architecture. And this isn't an either and or conversation. We assume internet style networking will exist for a long time, but this is an emergence of a new paradigm with a good Ethernet cost point for tackling several emerging problems in distributed computing and scale. So again, just to go one level deeper on the technology, if you look at the gray box on this slide, it's just an Ethernet data plane. It has ports like ingress port A and its egress port B, or at port 1 would be ingress A, egress B. You have packets arriving, and the control plane, which can live anywhere, it doesn't have to be on the box itself, it can be, and is potentially talking to not just one switch, but 10, 100, or 1,000, or even 10,000 switches, can send a signal to that gray box and say, for these matches, and those of you in the Erlang community already are very familiar with matching as a fundamental primitive, so that's very nice, and one of the reasons we liked Erlang for this application. For these matches, do something with the packet. If you match, do some sort of action, so you have match action rules, and then send it out port B. So it's extremely simple, really a remote programming interface to OpenFlow. I mean, to Ethernet. OpenFlow being a remote programming interface to Ethernet. So now all these flows become part of a programmable fabric, Ethernet fabric, and that puts the power of programming the network in the software layer, which is going to be much closer to the application, and really can be at some level of abstraction the application programmer themselves. Of course, that will require new tools, new compilers, new debuggers, new abstractions, but I think the paradigm shift is most programmers who write client-server applications have the most trivial network, right? It's just, I have a client, I have a server, and really my network looks like a wire. In the distributed sense, I already have 10, 15, 100, 1,000 nodes. I want to have control over that abstract network, the connection between those things, and great properties. And OpenFlow allows us to do that at the right kind of cost. Steve?
Thanks, Stuart. Is this? I just want to check this webinar box isn't actually showing over to the top of the slides. It is. Okay, thanks everyone. This concept of decoupling the control plane from the data plane is actually not a new one. It's very much history repeated. So the telecoms world has done this actually twice, in fact, but it certainly did it 30 years ago. The concept of separating the control from the data actually enabled service creation in the telecoms world. It actually created things like free phone numbers, and eventually it led to the mobile phone network. So actually gave the addresses kind of mobility. And I think the same kind of separation from control and data in the IP world is potentially going to lead to very new services created in the IP space and innovation. So effectively, what difference does actually data and control being separated make? I think Stuart's already touched upon it, that there's a large number of boxes have actually proliferated into the IP world, such as firewalls and so forth, which are effectively actions or policies applied to manipulation and control of data. So actually, fundamentally, they're doing the same thing at the data layer. They're moving packets from one port to another and applying rules. And yet it's the complexity of the control layer which has actually generated all these different types of boxes. As a result, we should see much simpler networks in the data layer, and moving the intelligence to the control layer will allow innovation to increase. So for instance, if we take traffic processing today, if we have traffic which requires low latency, today we tend to introduce things like load balancers and so forth to identify that traffic and route it in a different way. Today, when we move to an OpenFlow type network, we don't need to do that. The actual control layer can identify that the traffic needs particular handling and can route traffic in a particular way using exactly the same underlying data hardware. We don't need to do anything special about it. Again, if we look at things like denial of services attacks, particularly distributed ones today, in our kind of hardware-defined networking model, it's actually a very difficult thing to intercept and basically plug all the holes that the attack might be originating from, because it's done on a box-by-box basis. If we move to a software-defined networking model, that's something that can be applied at the control layer and can be applied ubiquitously across the network. So it actually leads to a much simpler approach to defending the network. After all, firewall is actually a function, not a box. So you're probably wondering, okay, this OpenFlow stuff sounds good. How do I go about learning about it? So the most simple thing to do is actually go and build your own. And this is where the link switch developed by Erlang Solutions comes to the rescue. So the good news about software-defined networking is that there are free to use OpenFlow switches available. And so you can actually build your own OpenFlow switch using inexpensive hardware. And there are two parts to this. So there's the switch and the controller, and just as well there are also open source controllers available too. So you can actually go and build effectively your own open source network to go and build and experiment with. I'm not going to go into all the detail on this slide, but in broad terms we can classify these OpenFlow products in a number of categories. One is educational, so that's exactly the tactic I'm approaching at the moment, which was you're a newcomer to OpenFlow, you can go away and build and experiment with networks. The others is a kind of prototype, which allows you to build more targeted towards hardware vendors, to actually build a prototype type platform to build viable products from it potentially. Bootstrap has a similar kind of activity, but they're much more optimized for data path activities, so faster traffic flows. And virtualized switch, which would be deployed typically in, say, a data center or a virtualized environment, giving software-only switching. This table illustrates basically the four principal open source switches which are available today. The first is OpenVSwitch, which was funded by VMware. There's Indigo 2, which is via Big Switch, SoftSwitch via Ericsson Research, and of course Link, the most important one, funded by or bootstrapped by Infoblox. So today we're going to talk about Link, which is an Erlang-based switch. The key characteristics is that it is a level of protocol support with two protocols. There's OF, stands for OpenFlow, and it supports versions 1.2 and 1.3, 1.3 being the most recent. And a configuration protocol, which is OFC, OpenFlow Config Protocol 1.1, which it also supports. The beauty of Link, because it's written in Erlang, is it exploits the multi-core capability, and it's very portable. So at one extreme you could actually build an OpenFlow switch on, say, a Raspberry Pi. So you could build the cheapest OpenFlow switch in the world by using Ethernet to USB ports. So for around £50 you can build a 4-port OpenFlow switch. It also runs on much more expensive multi-core hardware through to things like the Tylera card. So the link switch was developed by Erlang Solutions. It's completely free to download and use. It's been issued under the commercially friendly Apache 2 license, so it's perfectly possible to go and build commercial products off the back of this. And as I've already mentioned, it supports all the latest versions of OpenFlow standard. And it runs on a lot of hardware because of the flexibility of Erlang. Erlang has a number of carrier-grade characteristics, which means it's well suited to building robust, resilient switches. In terms of the choice of OpenFlow controller, again, there's a range of controllers out there available. Floodlight is available, which is from Big Switch. Beacon, which was originally written by Stanford University. Roo, which is written in Python by NTT. And there's some other controllers out there as well. So it's very simple to go away and build your own network using, say, the link switch and OpenFlow controllers such as Roo. So if you want to get out there and get started, right at the beginning you may have seen a logo with a rhino. That's the flowforwarding.org. So the flowforwarding website, flowforwarding.org website, is a community website promoting the link OpenFlow switch. If you go to this website, you can download the software to build your own switch. And so, for instance, if you wanted to use the Floodlight controller, you can go to projectfloodlight.com website to download the controller. So, in summary, OpenFlow is a new model for IP networking. The key principle of it is to decouple the data plane and the control plane, and that enables a shift from a box mindset to a function mindset. There's plenty of choice out there to go and build your own network from switches and controllers, and Erlang Solutions can provide support and customization to link if you require it. We'll now move on to questions.
Well, thank you for that, and I'm sure we'll all join in thanking Stuart and Steve for a very inspiring talk on OpenFlow. We've had a bit of a flurry of questions here, and the time that we have available will allow us to answer 4 or 5 of them, but we can certainly follow up and we'll answer all your questions following the webinar in written form. Now, to start with one of those questions, firstly, Stuart and Steve, could you please comment on the following? Stephen from the audience is asking whether you see Erlang being used across further OpenFlow projects outside of the link switch, and also wonders why would that be a particularly good thing, and what are the sort of benefits of using Erlang in the world of OpenFlow?
So this is Stu. I mean, I think partly, the question is, will Erlang be used outside of just the link switch with respect to OpenFlow? So I think that largely depends on you know, the people on this call and the community, and whether those who are familiar with it. It's unlikely in the short term that folks who are very familiar with software-defined networking as it stands today and very familiar with networking as it stands today are going to run to adopt Erlang. That has, you know, I think that over time, as we demonstrate the power of Erlang in any kind of distributed application, networking or not, you know, I think that has a good chance of happening. I think what the Erlang community has is a platform which is actually designed for networking, has primitive like the bit syntax and the matching kind of philosophy that is just perfectly made for OpenFlow style networking, and a problem set in, you know, if you think about large scale Erlang applications, wouldn't it be nice to have more flexibility, more properties that an Erlang, you know, OTP programmer had in terms of controlling the network. So I think there's certainly huge potential for Erlang to be part of OpenFlow controller architecture, because obviously while the controller looks centralized from a kind of a logical model, in the same way, say, the domain name service looks centralized in many ways to the app, it's clearly can't be centralized. It must be a fully distributed system. Any robust, scalable controller must itself be distributed, and Erlang seems a perfect platform to develop such things. So I think both from the potential use cases in distributed computing that Erlang community already is involved with, and the properties of Erlang itself, I personally hope that Erlang becomes an important part of the open source ecosystem around OpenFlow, much above the switch layer. But I think that'll be largely up to the folks on this call and the Erlang community, and the open source community, and embracing that idea and developing controllers and tools and tool chains on Erlang focused in this area.
Thank you, Stuart. To move on and try and answer a couple of other questions, we have had a query from Marcus, basically asking whether there are any example use cases for SDN within the service provider arena.
Sure. I think the most vocal service provider in support of OpenFlow software-defined network, OpenFlow-based software-defined networking has been Verizon, and to some extent Deutsche Telekom. Stuart Elby, the CTO of Verizon, has been, if you go search, I think you can look for Stu Elby, Verizon, CTO, OpenFlow in Google. I think you'll see some presentations he's made and other things that basically say cost-effective traffic management and network control for a service provider is actually so critical that if they don't have OpenFlow deployed in a reasonable amount of time, their entire business model is threatened. So from a service provider standpoint, I think the general consensus is here's an industry where the whole business model is I'm going to invest in a network and then monetize it over time. And if the economics are not right, then that business model is fundamentally threatened. So I think for service providers, which are one of the most vocal groups right now, software-defined networking presents a critical shift in economics and the way they do business. And so I think what we see in SDN is both service providers and high-density data centers tend to be the early drivers and early adopters of software-defined networking. And traffic management being the kind of core use case in the telecom side, service provider side.
I think OpenFlow has the potential to lower the price point for networking, and I think that's probably one of the key attractions initially for service providers, is that it provides a new layer or a new opportunity to improve their profitability.
Fantastic. Well, thank you, Stuart, and thank you, Steve. The questions keep pouring in, and I'd like us to address a couple of them. Here's an interesting one. We basically have a question about performance. So, for example, if box A is capable of running a certain number of rules, but box B is capable of doing just half of that, how is this addressed within the common control plane?
Yeah, so I think this is one of the most exciting things about software-defined networking is for the first time ever in the history of networking, we may be at a point where price and programmability are more important than performance in the same way that that's now been true in the server business for 15 years. And so specifically to address the kinds of technical issues you're talking about, OpenFlow fabric says if I have an Ethernet fabric which has n boxes, right, 100, 1,000 boxes that are connected by Ethernet, and they all presumably have even potentially different speed interfaces at the Ethernet level and different amount of processing power, and at any given time different amount of load, but we have visibility to the application, so we really understand the requirements of each individual flow. OpenFlow gives us a way to remotely program that Ethernet fabric to make sure that if 3 if three apps that are talking need a level of service that's required and one box in the flow path is not going to be able to give it, they just redirect the flow to different boxes. And that's not a new concept. We've seen this kind of fabric-based control in InfiniBand and asynchronous transfer mode. What's different about OpenFlow is that it's based on Ethernet, which makes it extremely cost effective, but that kind of typical attack on fabric style application-driven networking is still relevant and important in OpenFlow deployed networks.
Thank you for that, Stuart. Here's a question that goes into the very heart of the matter and sort of addressing the advance of OpenFlow. Can you cite an example of a small deployment being used in production within a commercial environment?
Sure. Microsoft Azure uses OpenFlow in a commercial environment. Google uses OpenFlow in a commercial environment. And then in the US, there are many campuses, including Stanford, Indiana University, that have full-blown OpenFlow-based networks as their production network. The computer science department in Stanford, and again, remember that's where even campus-wide TCP/IP came into play, and Cisco was born out of. The computer science department in Stanford has been running production OpenFlow for a few years, and now that's getting rolled out across many different departments. Same with Indiana University, has had a campus-wide OpenFlow production network run by Matt Davies for several years now. So we're well past the kind of science experiment, very early adopter phase, and have plenty of very robust commercial experience with OpenFlow today.
Thank you for that. Here's a question from Richard. Are there any specific hardware requirements to run Link? Can you do this through any Erlang-capable platform?
Yeah, it basically just needs to be hardware that supports Erlang. So if you can load Erlang OTP onto it, it will run. The key thing to be useful is it needs a number of Ethernet ports, because if there's only one Ethernet port on, say, a desktop PC, it's not particularly useful. So I built an Erlang Link switch using a Raspberry Pi. So that's a £25, $40 type piece of hardware. That only has one Ethernet port. So what I did was buy 4 Ethernet to USB adapters, and suddenly I've got an OpenFlow switch. It's for around £40 to $60.
That's a really good example. Now, here's another question that's quite interesting, coming from the telecom sector. Will it be possible for the telecom operators to use SDN with their parallel network? If yes, where should companies start from?
With a parallel network? Is that the question?
Yes. Yeah, exactly. So basically, will it become possible for the telecom operators to use SDN using their parallel network? And if so, where should the company start from?
That kind of implies it's a parallel network rather than integrated with the existing hardware, which it may make sense to do that. I think in a telecom environment, if I look at, say, mobile operators, the challenge that they've got is declining profitability and increasing levels of traffic. There also has ended up a lot of complexity in the network, largely because of this hardware-defined networking model, which drives costs. So, pretty much if your traffic doubles, the number of auxiliary boxes that you need to handle that traffic also doubles. Whereas I think the economics and the logic of an OpenFlow principle, it means that it doesn't necessarily have to be that way. You don't need double the number of boxes to achieve that. It also simplifies the layer of control. So I think the evolution from, let's say, a legacy network to one that's initially a hybrid through to eventually an OpenFlow will obviously require lots of intellect and intelligence to achieve that. But I would say probably the easiest place to start is localized. data centers would be an obvious place to start with.
Yeah, and I'll just add again, I think one of the best things to do, and it's really possible. I mean, it reminds me of the exciting times of getting Linux running for the first time, is do exactly what Steve said. Build your own OpenFlow switch with, very inexpensive network white boxes and open source, which is freely available. And I think immediately you'll see some of the powers, which is because you're just programming an Ethernet data path. That's all you're doing, remotely programming an Ethernet data path for match action rules. You can easily just make any port to port flow, the Ethernet data path itself, the OpenFlow data path itself, can just be a wire at first. And then you can make it a tap. And then you can see what kind of performance is there. And then do you want to actually change a packet? So I think the nice thing about OpenFlow as a starting point for software-defined networking is, instead of having to think about the overall architecture and how we do it today, you can say, I can insert these network white boxes in strategic places and start doing really value-added applications in an incremental way at a very low cost point. And that's why I think starting with OpenFlow is probably the right place for any organization, telecom or otherwise, to really understand where the value and the economics are going to come in for software-defined networking.
Thank you both. We will try and make time for 2 to 3 more questions. Here's one for you, Stuart. One of our members of the audience is wondering, what are the top use cases that Infoblox wants to address with its SDN strategy?
So we don't have any, Infoblox today has no SDN products. I want to be clear about that. We're not an SDN company. We've been in the business of network automation for 13 years on hardware-defined networks. We're one of the very few companies in the world that has sold independent software into the networking industry. We're really a software company in the networking industry. We don't and have never sold any packet processors in like a router, switch, or firewall. We sell solutions at the kind of control plane layer of hardware-defined networking. But by control plane, we mean really the endpoints, the applications that are interacting together. So we do things like DNS and DHCP and IP address management. And that's software, which we sell sometimes with a server, but that's just a server. It doesn't do packets. So we're really a network automation company at the control plane level and hardware-defined networking. We think that software-defined networking is, again, a paradigm shift where the value in the hardware below where the solutions we have is moving from hardware to software. So that's like the end of the mainframe to PCs and servers, and that changes, it gives more value and more flexibility in the packet processing layer for our customers today. We've got about 6,000 customers worldwide, mainly focused on the larger enterprise. And so, we stand kind of as ready as a trusted advisor as this paradigm shift in economic change happens in networking, so any organization can rationally adopt a more software-defined strategy, because it's not going to happen. I mean, hardware-defined networking is not about technology. It's an entire industry organized along box function lines. It's the way the vendors are organized, the analysts are organized, the press is organized, it's the way the channel is organized, and it's the way teams are organized inside all of our customers. So you have a firewall team, a load balancer team, a router, and we don't think that's a bad thing, and we don't think that has to change overnight. We think that there are new opportunities for that to change in a rational way as the business needs it, that software-defined and give better economics over time, that software-defined networking is really a huge paradigm shift, but that's going to require some kind of help in getting there. And we deeply understand the current way the networks are structured. We've been focused on network automation from the beginning, so we think what we're trying to understand is how do our customers, the market at large, migrate rationally or transition rationally from the current hardware-defined network to a more software-defined network going forward? And we don't know yet. That's one of the reasons that open source and all the kind of hands-on experimentation seems absolutely so critical to us, and the reason why we're willing to support that and fund that through organizations like Erlang Solutions.
Fantastic. Thank you for that, Stuart. We have time for a single question that is left, and I'll ask that question to you both. What OpenFlow controllers are commercial users using at this moment? For example, Google, Microsoft Azure. Are they perhaps developing their own?
Yeah, so I can't speak directly for them. I can only kind of speculate. I have some knowledge of those things, but I think you can imagine, in the same way that they've built all their own infrastructure, that yes, that primarily those organizations have built their own controllers. And I think that's one way to think about where we are with software-defined networking. We're just at the beginning, because as software-defined networking and OpenFlow become mainstream, as network white boxes like the Intel Seacliff Trail platform become available, more available in the market. That's a OpenFlow supported network white box you can buy from companies like Quanta and ADI Engineering. As that network white box ecosystem emerges, the mainstream organizations, enterprise telcos, are not going to build their own. They're going to look for products, open source, vendors to provide that and help them get to be a little bit like an Amazon or a Google or a Yahoo. Most organizations don't want to be the largest search engine company in the world, but they want to have products that allow them to have better efficiency and economics in this networking space. So we think that's exciting.
I think what's really interesting is that the value of networking is moving to the higher layers. So something sitting above the controller may have the highest value. So maybe there's going to be something like an app store that sits above the controller, and people can buy load balancing apps or whatever. And I think that's the really interesting area, that there's actually a complete shift which will allow that kind of innovation to emerge.
Fantastic. Well, thank you for that. Now, to close off, I'm sure that you will all join me in thanking Stuart and Steve for a very inspiring talk on OpenFlow. Many thanks to all of you who have joined us for the webinar as well. Please join us again end of June for our next webinar, which will be dealing with payment switches and environments challenged by the need for extremely high throughputs of concurrent transactions. You will have a chance to hear about the developments to date and the work Erlang Solutions have been doing in developing Erlang-based payment switches for organizations that critically underpin UK's bank payments infrastructure. On that occasion, we will have Sean Hodgkiss, the Technical Director at Tutuka, and Rudolf van Graan, one of our own lead architects with years of experience in payments, which is joining us and sharing their insights on the topic. We will be sending you a short survey to make sure we capture your feedback of today's webinar. Please also note that the recording of today's webinar and the accompanying slides will also shortly be available for you to collect on Erlang Solutions' corporate website at www.erlang-solutions.com. Thank you once again, and we look forward to seeing you again on our next webinar.